Ladies and gentlemen, let me present our combined approach to detection of the dissipative structures which emerge during irreversible ground movement. We consider the dissipative structure as the metastructure due to the organizing of energy flow. This is the theory for organizing energy flow in operation and conversion under material dissipation. We discuss this problem of the dissipative structure detection during irreversible process in geomechanics. Then we show importance of the precision used during irreversible ground movement monitoring. Then discuss combined approach to detect dissipative structure, show a practical example, and make a conclusion. An apparent dissipative structure may be registered during the yielding of clamps in the frame support that resists to ground pressure and provides stability of an underground tunnel or a roadway. It is so-called a stick-slip friction, when the frame resistance can change by 2 to 4 times. Finally, the frame may fail. Quasi-periodic roof caving of powered support fluctuation in a long may appear as a dissipative structure. These processes are dangerous and may damage the support or terminate longbow operation. There are other irreversible processes which are important components of energy extraction. For example, gas, hydrothermal energy, etc. This is hydraulic fracturing. According to the theory of thermodynamics, hydraulic fracturing must generate dissipative structure, but they are hard to detect because an intensive uncertainty noise. This slide demonstrates distribution of ground movement during landslide development. The fields of vectors show some structures. The separate ground fragments move in different directions, namely downward and right, and downward left. Is this underlying pattern or random noise? We do not know yet. Different fragments may move dissimilarly, and some trajectories of their fragments are in limit of the measurement error. Besides, the results may depend on the measurement schedule of how often the data collecting is made. When interval between serial measurements is big, we may lose the valuable information. On the other hand, the monitoring is inexpensive and too frequent measurements may be rather costly. We proposed to use variogram method to test if there are some clusters in the cloud of initial data. If yes, we use Kamins method to detect the clusters. Method Kamins has been used to simultaneous variance minimization of distances between vectors within a clusters and maximizing of the distance variance between the clusters centers. We start from two clusters and then increase them gradually, checking the entropy through the variance. When the variance of the distance stabilizes, we terminate the process of clustering, minimizing the entropy variance within the clusters and maximizing between them correspondingly. This is an example that demonstrates the developed method on the ground subsidence case around moving longbow. This is a physical model. Rock mass moved irreversibly during the longbow advance. The roof caved periodically. This slide demonstrates vertical ground subsidence and incremental vector distributions between serial or sequential positions of the longbow. Measurement of the fragment displacement were made in such a way that the increments were in the range from 2 to 5 standard errors of measurements. Next slide demonstrates the distributions for the next position of the longbow and results of the clustering. The clusters overlay as usual. That is why we propose to employ Voronoi tessellation to locate the boundaries of the clusters. The dramatic difference between the displacement distribution is that all vectors are oriented downward and to the left of the gob in previous figure, whereas they turned to the right of that phase at the next step, which was increased by only 4 meters. In addition, the area of the rope mass expanded, where the incremental displacements were detected with the confidence of more than 90%. Such a difference is not random and may be explained from a physical point of view. The maximum incremental displacements occurs in the zone of maximum sag and possible delamination of the rock layers. And now conclusion. The combination of the variogram algorithm, K-means method, and Voronoi tessellation or mosaic provide reliable clustering of the irreversible ground movement and detection of dissipative structures. The developed method of dissipative structure clustering has been tested successfully in the case of irreversible ground displacement around moving longbow phase. The new method not only revealed specific patterns of the dissipative structures, but complied with the physical sense of the irreversible ground movement. Thank you for your attention.